Two circuits are placed side by side as shown in the picture. Each circuit has a coil. The circuit on the left hand side has coil A. The circuit on the right hand side has coil B. The circuit on the left hand side has a switch and it has an EMF source as well, whereas the circuit on the right hand side is just made up of a wire, the coil, plus a resistor. We will use Lenz's law to determine the direction of the induced current in the circuit on the right hand side for three different cases. In case 1, the switch is opened after having been closed for a while. While the switch was closed, there was current in this circuit on the circuit in the left hand side, and the direction of the current was like this. Remember, the current leaves the positive terminal of a battery, so the direction of the current before the switch is opened looks like this. Using the right hand rule, let's determine the direction of the magnetic field created by coil A while the switch was closed. Curl your fingers in the direction of the current. Your thumb points in the direction of the magnetic field. So while the switch was closed, there was an existing magnetic field pointing to the right. Now when we open the switch, that magnetic field goes to 0. What happens to coil B? Well, while the switch was closed, there was magnetic flux through coil B, again pointing to the right, and the magnetic flux goes to 0 when the switch is opened. So the magnetic field, originally pointing to the right, decreases. The response of the coil will be to create an EMF, that's the induced EMF, to compensate for the loss of the magnetic flux. Because the magnetic flux is decreasing, the coil will create a magnetic field in the same direction to put back the loss of magnetic flux. So then the induced magnetic field will be pointing to the right. So this is the direction of B induced. In order to create a magnetic field pointing to the right, what must be the direction of the current in coil B? Again, let's use the right hand rule. Align your right thumb in the direction of the induced field. The direction of the curling of your fingers point in the direction of the induced current. So based on the picture, that should look like this. Now, what must be the direction of the induced current in the resistor AB? It should be pointing from left to right, following based on the direction of the current in the coil. So if we open the switch after it was closed for a while, there will be an induced current in the circuit on the right hand side, and the direction of the current on the resistor AB will be from left to right. Case 2. Coil B is brought closer to coil A while the switch is closed. As we said before, if the switch is closed, there's a current on the left hand side circuit, like so, in the clockwise direction, leaving the positive terminal, and this is the direction of the current in the coil. Based on the right hand rule, if we curl our fingers in the direction of the current in the coil, our thumb is pointing to the right, so the existing magnetic field is pointing to the right. Now there's already a flux, magnetic flux, pointing to the right in coil B. What happens when we bring coil B closer to coil A? The flux will increase because both of the coils, or any coil that has current in it, will act like a bar magnet, right? If you get closer to the coil, the magnetic field becomes stronger. Because magnetic field becomes stronger when you get closer to the coil, then the flux going through coil B will be greater as it's getting closer to coil A. So then the flux through coil B, that points to the right, is increasing. the coil will respond to that by trying to decrease the flux, because the effect will be oppositional. The magnetic effects are always oppositional. The induced EMF is always oppositional. So because the flux through it is increasing, the coil's response will be to create a magnetic field in the opposite direction. So in this case, the induced magnetic field will be pointing left. This is the direction of B induced. Now let's determine the direction of the induced current in coil B. Align your right thumb to the left. The curling of your fingers show the direction of the induced current. So it will be like this. And in the rest of the circuit, the induced current will be in the clockwise direction. So at resistor AB, the induced current will be flowing from right to left, in other words, from point B to point A. Case 3, the resistance of resistor R is decreased while the switch is closed. Again, while the switch is closed, on the left-hand side circuit, we have a magnetic field pointing to the right. If we decrease the resistance, that will increase the current in the circuit. If the current in the circuit increases, then the magnetic field will become stronger in the circuit. So the magnetic field will increase. How does that affect the coil on the right hand side, coil B? Now, initially coil B has flux going to the right, pointing to the right. Now that the magnetic field strength is increasing, the flux that is pointing to the right will increase. And again, to oppose that effect, coil B will create an induced magnetic field in the opposite direction to undo that change. Basically, the flux is increasing, the coil will create an induced field in the opposite direction in an attempt to go back to its initial state. So the induced magnetic field is again pointing to the left. By the right hand rule, the direction of the induced current in the coil looks like this. And the direction of the induced current in the rest of the circuit is again clockwise. Therefore, induced current flows from B to A.